Hello everyone, my name is Li Donghui and my presentation is about the MAC layer protocol design based on a smart antenna in ad hoc networks. And my presentation will be divided into 4 parts. First, about what is the ad hoc network. As shown in the figure, mobile ad hoc networks are self-organizing networks that don't rely on fixed infrastructure. It is capable of fast temporary networking, such as in disaster recovery. However, it has some drawbacks, such as the limited shear bandwidth, so efficient use of channel resources has become very urgent. Based on the TCP/IP model, my research mainly focused on the bottom 2 layer. MAC layer as a sublayer of the data link layer mainly responsible for the media access control, determines the allocation and scheduling of network channel resources. Due to the numerous advantages of the TDMA, it is chosen to be employed in our system. Under the TDMA mechanism, channel resources are divided into time slots. MAC layer is to deal with how to allocate these time slots. And for the physical layer, smart antenna employ advanced beamforming technology compared with the omnidirectional antennas that can realize spatial radios. And my research is based on the smart antenna to design an efficient MAC protocol to maximize the network performance. Our system is depicted in the figure, and my study was to develop a MAC protocol in the mobile ad hoc network based on the smart antenna. And the network was designed specifically for long-distance wireless communication and not have a dependent devices to communicate with each other. And my work is design, simulation, and application of the MAC protocol in the network. And then it's about the MAC protocol. And the first is the frame structure. And in the TDMA frame serves as the unit for partitioning channel resource. And the frame structure can be like this. And for each TDMA frame, it can be divided into the monitor frame, data transmission frame, and slot allocation frame. They are work at the basic part of the frame. And for my work would mainly focus on the slot allocation process, so I will introduce this as a frame specifically. The slot allocation frame employs a request and response mode to illustrate the slot allocation process clearly, and the network nodes are categorized into 3 types. The nodes serve as the slot allocation nodes for the current frame and its neighbors and then it's the other nodes. And during the slot allocation section, and the neighboring nodes send a slot allocation request. Next, the slot allocation nodes calculate the time slot allocation, and finally, in this part, the SA node will broadcast the results. During the ultra-long transmission, where considerable propagation delay leads to numerous channel access conflicts. To solve this problem, the node send data in advance, but there is another problem. As an illustration considers 3 consecutive time slots in the transmission time slots 1 and slot 2. The node transmit a data packet with a lead time of T1 and T2. Finally, there will be a conflict as indicated by the overlapping region. So this is a problem we need to solve. And the second one is that the implementation of the spatial reuse interference may occur between different links sharing the same time slot. For instance, in figure, there are 4 nodes when link 1 and link 2 are transmitting data at the same time slot. When the two angles are smaller, you can see there will be an interference between the two links and will lead to packet loss. So to address these challenges, we proposed a state interaction-based allocation protocol. This protocol will utilize the interaction of node status to avoid those issues. So based on the node status, we update before and after slot allocation. Each node in the network has different status to their neighbors in different time slots during the data transmission section. As shown in the table, the local node represented in green is surrounded by neighboring nodes, the yellow nodes 1 to n. And the status of the slots includes 7 tabs. After 3 steps, we will determine the status of different slots. By the 3 steps, we will determine the final node status table to avoid the lead time conflicts between the two adjacent transmission time slots I mentioned before. And so for the challenging of the interference between different links sharing the same time slots, we adopt the interference avoidance strategy. Our approach is that after determining the slot status, we redetermine the blocking status to avoid the interference. And the process follows. Several nodes are in the network, and the green to the blue nodes employ the interference avoidance strategy at the slot 1. So if the status of the slot 1 from the green node to the blue node is indicating that green node can send data to the blue node at the slot 1, then the green node initiate the following steps. It will look up the latest time slot allocation results to find their existing wireless communication links at the slot 1. Then it calculates whether establishing a link to the blue node would interfere with other links. The calculation indicating includes determining the 2 angles as illustrated in the figure. If the angle is too small, indicating that the link between the green and blue nodes could potentially interfere with the reception node of the link C, so the green node update the status of slot 1 to transmission blocking. By this way, we can avoid the interference that may arise by the different links. So in this section, I will introduce the simulation of the system, and we conducted the simulation verification using the NS2 platform to test the performance of the MAC protocol. And there are 8 nodes, and all nodes can send and receive data from the other 7 nodes. So, firstly, the simulation system was designed to test the interference avoidance strategy on the network performance. So, in certain local areas, such as the node 0, 1, 2, 3, link interference could exist between the 2 links. First, the simulation was conducted to compare network performance with and without the strategy. Table presenting the slot allocation results from the time slots 15, 16, and 17 during the simulation time. And the highlight certain links, for example, the links to node 2 to node 0, and to indicate that they are interfering with other links using the same time slots, resulting in the loss of data packets transmitted. So by comparing the slot allocation situations in these two tables, we can observe a significant reduction in the interference between links after the activating the strategy. And in the tables for the spatial reuse, we can see simultaneously communicate for links in the time slot 15 achieving the maximum of spatial reuse within one hop range in the network. For the final two columns in the tables indicated that before activating the strategy, the network allowed 230 communication links, and out of which 17 instances suffered interference. However, with the interference avoidance strategy, and the network supported a total of 230 occurrence of the communication links, with only 4 links interfering within the network. This represents a decrease of the 13 occurrence compared to the activation of the interference avoidance strategy. So after not activated the interference avoidance strategy, we test the overall performance of the network. First figure depicts the network throughput comparison between the spatial reuse and theoretical throughput without the spatial reuse. And you can see that after our network can perform a higher throughput with the spatial reuse. And then is about the node throughput. We can see that the throughput of the A node remains relatively consistent, fluctuating within a small range when the network is stabilized. The figure shows the end-to-end delay for the 2 links in the network. We can find that the link delay is smaller than 0.02 seconds. And the final figure is illustrate the CDF of the 2 links delay, indicate the over 90 of the data packets in the network experienced a latency below 0.015 seconds, which demonstrates that the network node can conduct normal communication without any issues. So finally, it's the conclusion of my today's presentation, and I designed a Mac protocol based on the smart antenna. It includes the TDM A-frame structure, the process of the slot allocation, and the latest interactive process. And second, I based on the Mac protocol operate the simulation, and the interference of the avoidance strategy can greatly reduce the interference between different wireless communication links. And then the network can realize high performance communication with spatial reuse. So that's all my presentation today. Thank you for your listening.